Hello everyone, I'm Min from MIT. Today I'll be telling you about learning sleep stages from radio signal using a conditional adversarial architecture. This is joint work with Shichao, Dina, and Tommy from MIT, and Dr. Bianchi from Mass General Hospital. We all live in the sea of wireless signal. For example, you are now sitting in a conference room in Sydney, surrounded by Wi-Fi, cellular, etc. What if somebody comes and tells you that such wireless signals can be used to understand when you are dreaming, when your brain is consolidating memory, or more generally your sleep stages? How can we do that? Is this even possible at all? This is exactly the topic of my talk today, and I'm going to show you how we can use wireless signals together with a new model to nurse sleep stages without putting any sensor on your body. Let me start by telling you something about sleep. When we go to sleep, our brain activities change and our sleep enters 4 different stages: awake, light sleep, deep sleep, and rapid eye movement. Different stages of sleep are associated with different physiological functions. For example, dreams happen during REM sleep. While deep sleep is associated with memory consolidation, light sleep is associated with cognitive processing. Now let's look at sleep stages from one night of study. It progresses in cycles and will enter and leave different stages multiple times throughout the night. Monitoring the temporal progression of sleep stages is very helpful for understanding many diseases. For example, sleep disorder, depression, Parkinson's, and Alzheimer's. However, monitoring sleep stages today is very difficult. It's typically done in hospital with many sensors and electrodes on the body. In fact, I do have sleep problems, and let me show you my experience going to a sleep lab. What you are going to see next is a video of sleep technologist who is setting me up for one night of study. After that, I have to sleep with all these sensors in a bed that is different from my own. You can easily tell from my face that it wasn't very comfortable with all these sensors and cables. At the end, I had a hard time falling asleep. Then I started thinking, can we do it in our own bedroom, without any sensors or electrodes on the body? This is exactly what we did. Here you see our device. It transmits a very low power wireless signal that reflects off the person's body and comes back. We have a new adversarial model that analyzes these reflections and spits out the sleep stages over time. The contributions of this work can be summarized as follows. We deliver a new application that predicts sleep stages accurately from wireless signal without any physical contact. In order to do this, we developed a new model that introduced conditional adversary for domain adaptation. Finally, we conducted 100 nights of sleep study and released this dataset to facilitate future research. Before I can tell you how the model works, I have to tell you something about wireless signal. In the past 5 years, there has been a lot of research interest in the wireless community, trying to extract physiological signals from wireless. The idea is very simple. When you transmit a wireless signal, it reflects off the person's body and changes with his breathing and heartbeats. Therefore, by analyzing those reflections, you can monitor his physiological signals. Indeed, prior to our work, there were proposals to use wireless signal to extract information about sleep. However, the accuracy was low, around 64%, which wasn't enough to replace on-body sensors. And it mainly focuses on detecting motion and is limited to a single environment. Our objective is to achieve high accuracy that is on par with sleep lab, but in our own bedroom, without any sensor on the body. The key challenge in doing so is that RF reflections are highly dependent on the measuring conditions and the individuals. First of all, RF signal not only reflects of the human body, but also reflects of everything in the environment, including walls and furniture. Therefore, the RF reflection we are looking at is different for different environments. The RF reflection also varies across different individuals. In order to get accurate sleep stages, what we need to do here is to remove such extraneous information specific to measuring condition and individuals. In a sense, this is a form of multi-source domain adaptation, where each domain is a specific combination of a measuring condition and an individual. The problem of RF reflection being highly dependent on the domain is that the signal from different domains have very different distribution, and therefore the machine learning algorithm cannot generalize very well. What we need here is a representation of RF signal that is more or less the same across different domains, and therefore the learning algorithm can generalize better to new domains. When we started looking at this problem, we were motivated by recent advances in adversarial training, which provide a basic framework to think about a solution. Specifically, we want to find a representation of our signal so that we can predict the sleep stages. But at the same time, we want the extraneous information to be removed from this representation. So how can we do this? The idea is to introduce an adversary here, which is trying to predict the domain based on the encoded representation. At the same time, the encoder tries to prevent this adversary to succeed, and therefore, the encoder will remove domain information. The training of this model can be viewed as a game, where the value function is defined as the loss of predictor minus the loss of discriminator. During training, the encoder and the predictor are trying to minimize this value function, while the discriminator is trying to maximize it. Okay, are we done? Unfortunately, this is not a good model for our task. The problem is that the discriminator can remove both extraneous and useful information. This is due to inherent correlation between stages and domains. For example, it might be that being obese affects sleep staging. Thus, knowing whether someone is obese can be helpful in predicting sleep stages. But in the current model, the discriminator will force the encoder to remove such information. So, how would you solve this problem? The idea is simple. Since we want to prevent the discriminator from removing information relevant to sleep stages, so we just give it that information as input. That is, we give it the posterior label distribution. Now the encoder cannot fool the discriminator by removing this information because the discriminator will always have it. So, this gives us a conditional adversary model where the discriminator is conditioned on the posterior label distribution. The difference between this conditional adversary and the original one is that, while the previous adversary is trying to ensure independence between the encoded representation and the domains, our conditional adversary is trying to ensure conditional independence between them. This conditional independence facilitates accounting for inherent correlation between stages and domains. But it's not that simple. We don't have the posterior label distribution during training. So how can we train such a model? Here's the solution. We approximate the posterior with the predicted label distribution and simply condition the discriminator on the output of the predictor. Now the question is, does it work by condition on the predicted label distribution? The answer is yes, it works. In the paper, we proved the following theorem, which I state here informally. Given enough capacity, the encoder at equilibrium discards all extraneous information specific to domains, while retaining the relevant information for the predictive task. Now let me tell you the evaluation of our system. We installed our device at 25 different homes and collected 100 nights of sleep studies. During each night of study, the user also wears an FDA-approved EEG-based sleep profiler, which gives us sleep stage labels. After all, we got over 90,000 30-second pairs of RF measurements and stage labels. This dataset is used to evaluate our model, and it also has been released to facilitate future research. Remember that our goal is to achieve high accuracy on par with sleep lab. Of course, we want to improve over previous solutions that have an accuracy over 64%. But the question is, how far we can go beyond that? It is important to know that labeling sleep stages is subjective. At the sleep lab, sleep technologists look at the signal and manually label sleep stages. If you ask two different sleep technologists to label the same night of data and compare the results, the inter-reader agreement will be around 83%. So our goal here is to go from 64% of previous solutions to somewhere near 83%, which is on par with sleep technologists. Now let me show you our accuracy. It is almost 80%, which is pretty close to the accuracy of sleep lab. Also, this is the accuracy when testing on new subjects that we haven't seen in the training set. That is, this is a new domains. Let's also compare the kappa coefficient with past work. Kappa coefficient takes into account the possibility of agreement occurring by chance, and therefore is a more robust metric. As you see here, the kappa coefficient in past work was low. This is because the classes were unbalanced, which made the classification easier. In contrast, our model achieves significantly higher accuracy and kappa coefficient. Let me now show you a representative example. This is the same night with the same person. The top graph shows his sleep stages as a function of time predicted by EEG sleep profiling. The bottom graph shows our prediction. As you can see, those two results match with each other pretty well. In fact, their accuracy is 80%. Also, the differences are mostly due to fast transitions, which are typically ignored by the doctors. But remember, the top graph requires the person to wear EEG electrodes, while the bottom one allows him to sleep comfortably in his own bed. Finally, I want to show you that our accuracy is high for all the subjects and all the environments. Here you see the accuracy for 25 people in our experiment. As you can see, it works well on all of them. This means that our model can generalize well across all the domains. So in today's talk, I have told you how we can learn sleep stages from wireless signal. We believe our work can be extended along multiple axes. On one hand, this model itself has implication beyond sleep staging. It can be used for other types of healthcare data where there's a strong need for generalization across individuals. On the other hand, being able to monitor sleep, as we discussed earlier, can be used to understanding the connection between sleep and many other diseases. We are currently working with medical doctors on this. Thank you very much. I'm happy to take any questions.